Okay guys, so we're going to start on the measurements and calculations notes. These notes up here you have already done because they were over ions and isotopes in that last video we did. So now we're going to talk about measurements and calculations. And these are kind of general measurements and calculations in science that you probably are familiar with in other science classes, but since we will be using them a lot in this class, I made sure to go over them explicitly so that we have a little refresher before we actually start to use them. So the first thing with measurements that we're going to talk about is scientific notation. And scientific notation is important because it's a way to express very, very large or very, very small numbers in a manageable form. Okay? And it explains to us that it's written as a coefficient, which is just a number, times 10 raised to a power. So right here, for example, this number, which is Avogadro's number, and we will go over that in a lot more detail, but it's 6.02 times 10 to the 23rd is Avogadro's number. And basically it's a way to count how many molecules or atoms are in something. It's a unit of measurement for molecules or atoms, since we can't like individually count them like donuts or dogs or something. We just have this number that says this is how many there are. Boom, we figured it out. That's how many there are. And just from this number, we can tell that it is a very, very, very large number. And that makes sense because atoms are very, very small. So if we're talking about how many atoms are in a room, it's going to be a very, very large number of atoms. So to convert this number, you're going to write this example down for me. This number, Avogadro's number, written out is followed by 21 zeros. So we're going to write this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, and then that's our whole number, and then 0.0. Okay, so the decimal is all the way down here. But if you're like me and every other scientist in the world, you absolutely do not want to write this number every single time. So from this entire number, we can get this number. And so the way we're going to do that, the easiest way, and honestly the way I still do it, is to just count the number of decimal places. So say I just gave you this entire number and told you to put it in scientific notation. Still, honest to goodness, the way I do it is I just move the decimal over and count how many times I do it. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And now our decimal point is right there. So instead of writing this entire number with 21 zeros, we move it all the way over so that we get a nice and neat 6.02 times 10 to the 23rd. If you were going to do it the other way, and I give you this number, basically you just have to count, you have to move this decimal over 23 times, and then you'll get this number, okay? But it's not like I'm going to be making you do actual math problems using this number. Like, you won't ever have to multiply or add this number like on paper. Obviously, we have calculators for us, and that's what we're going to use. But there's a very specific way you have to enter this on the calculator, otherwise it will not work, okay? So on the calculator, get your calculator out right now, Or if you don't have a calculator, ask me for one because I have a bucket of them in the lab. So get a calculator and figure out which buttons you have to press in order to get your number in scientific notation. So if we were going to be entering Avogadro's number in the calculator, you would type it in this sequence, 6, and then a decimal, and then 0, 2, and then depending on your calculator, you either have a button that says EE or EXP, and you're going to hit that button and then type 23, and it'll put them in the exponent position. So your calculator could look something like this after you type it in. This is the good way to do it. Okay, this is the correct way. We're going to circle it in green because it is correct. Okay, this is good. And you'll notice down here that on this calculator, TIs, they typically have the EE button. And if you have, what is it, like a Casio or the other common brand, typically those have the EXP button, but either one, they should only have one of those buttons, and it means the exponent, okay? Scientific notation. You cannot enter 6.02 and then the multiply button, and then type out 10, and then insert the exponent 23. That will not, because of PEMDAS and everything, it will not multiply out the correct way that it should. The order of operations will be messed up because you entered it that way, and you will not get the correct answer. Okay? Another formatting issue we got to talk about is when you're writing those big numbers, like I did up here, Avogadro's number, you are not going to use commas. We'll underline that. Do not use commas to separate groups of 3 digits. That's what we were taught in elementary school, but that's not what we're going to do here in science. So you can see in this entire thing, I didn't put any commas. Because in other countries, say in Europe, they, instead of using decimals, they actually use commas. So if they were talking about like $1.23, even though they wouldn't talk about US dollars, but whatever, go with it. If they were talking about that, then they'd use a comma instead of a decimal. So if we use commas in America, it causes confusion on the international scale, so we just don't use them. Everyone in science has agreed to not use them. We just use spaces instead, so we do not do this. That's easy to read because that's how we were taught, but you can still group them in 3s, just kind of leave a little space, okay? And then, since we're already on a rant about Americans, let's talk about units, okay? So we're probably familiar with the fact that the United States has it differently, because whatever, we're one of 3 countries out of the 196 countries in the world that uses it, because we're stubborn. But in science, we do not use the U.S. standard. We use SI units, which stands for basically International System of Units, okay? There are definite advantages to this, even though as Americans we're kind of like, well, we don't understand it, so we don't like it. No, SI units make a lot more sense, so don't know why America is still using the U.S. customary system of units, but whatever, we're stuck with it. But in science class, we will be using SI units, and we will talk about, we'll fill in some of them down here. But the advantages, they're all based in tens. So for units, they could either be in tens or hundreds or thousands or 10,000s or millions. That way they're a lot easier for computation and conversions. And units of various quantities are defined in terms of simpler quantities, which we'll talk about in a little bit. But, so when we use scientific notation up here, we are using the SI units. Okay? So if we're talking about either really big or really small numbers, we can typically write them using the scientific notation or the SI units. So if we're just talking about 1, because we're said they're based in units of 10, or based in 10, if we're just talking about 1 and like there's no multiplication factor there, that is 10 to the 0 power, and that just equals 1, okay? And so, bear with me, I didn't leave a lot of room on my paper for this. I'll write it over here, actually. So that's kind of the middle ground. If the number is bigger than 1, it can be it could be 10 to the 1th. 10 to the first power is what I'll say. And that just equals 10. And that prefix, because we love our prefixes, that prefix is called deca. So we're going to write that once I can figure out how to write on this. Okay. Deca. You can arrange this better. This isn't really working because I didn't have a lot of room, but go with it. Okay. And then if our number is getting bigger, then we'll obviously have 10 to the second power. And we know that 10 to the second power is 100. And this prefix is hecto. Okay, and then 10 to the third power is now 1,000. And this one is probably a prefix you're more familiar with, and that's kilo. Like a kilogram or a kilometer. Okay, those are the main ones that we're going to talk about, the main prefixes when it's getting larger. There are other ones for when it gets smaller. So let's say we had 10 now to the negative first power. And this is equal to 1/10. Okay, so our numbers are getting smaller. And this prefix is deci, like decibel or decimal. Those are examples of decreasing by the power of 10. And then 2 is 1/100th. And this prefix is centi, which you might be familiar with centimeter, which is literally 1/100th of a meter, which is a base unit in SI, and we just add the prefix onto it and we know what it means. And then we have 10 to the third, or 1/1000th, and that's milli, like millimeter. And then we have 10, we're skipping around, there is 10 to the 4th and 5th, but they're not as common, or they can be as common, but typically the units that I picked the ones that I felt were important, okay? So 10 to the 6th is 1/1,000,000. But again, we're not going to use commas. We're just going to separate them a little so that we have them in groups of 3. And the prefix for that is micro. Which, if you remember your bio terms, what does micro mean? Small. And so this is just a pretty small number. And the last one we'll do is 10 to the 9th power. And if we did the math on it, we'd realize that it's 1/1 billionth of something. and that prefix is called nano. So if you have a nanometer, that is a very, 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 very small unit of measurement. And derived units are what we call basically a combination of those base units. For example, grams per milliliter, mole per liter, joule per gigakelvin. And you get these by combining them either when you're multiplying or dividing. Okay? And there are some rules when doing calculations. Most of them are typical math things. But the main thing is rule number 1, only like quantities can be added or subtracted. That's rule number 1. And there are basically no more rules that you probably haven't already been told. But the exception to that, because there's always exception to rules, are they do not have to be the same when you're multiplying or dividing, just when you're adding and subtracting. So, for example, you could easily add 17 milliliters plus 13 milliliters and get 30 milliliters. However, you could not add 17 milliliters plus 13 liters, even though it still has liters in it. It's not the same unit because it is not, it doesn't have the milliliters. This is a completely different unit than that one, even though it has like the same word and the same letter. This is a completely different unit because this one is a lot smaller, remember? There are ways, though, that we can add these or work with these numbers, and we'll talk about those later because conversions are a thing. So this one we cannot do. We can't add when they have different units. And then this one, we'll make it green. We can. That is good. Okay? Okay, so going down there, let's talk about uncertainty. So uncertainty is basically we have to talk about it because in science we can't be 100% certain of anything. I don't ever like using absolutes, so we can't say yes, this for 100% fact is what it is, okay? There's always that level of uncertainty because in science, do we know everything? No. So we can't be for certain on some things. And there are 2 types of uncertainty and certainty that we'll talk about. And they're probably words you've heard of but have never been defined for you. So the first one is precision. And so precision is the agreement between several measurements of the same quantity. Okay, so it's just the same quantity. If you're getting the same number over and over, or nearly the same number, that's precision. Okay, so the values are close to the average, meaning that if you average them all together, they're within a pretty close range. For example, 27.2 degrees Celsius, 26.9 degrees Celsius is only 0.3 degrees more. And then 27.1 is very close to all of those others. And that is precision, and we'll do a little diagram in a second. But the second type is accuracy. And accuracy, if you are accurate, it's the agreement between measured value and accepted or true value. So up here, for precision, it said nothing about the accepted or true value. It just says, hey, they're all pretty close to each other, okay? But for accuracy, you're trying to see how accurate you are. So let's say on this example, Density of gold is measured to be 19.2 grams per cubic centimeter. They measure it again and get, or a different sample or the same sample, whatever, and get 19.4 grams per centimeter cubed. And then they measure another sample and get 19.4 grams per cubic centimeter. And the accepted value, because we know, is 19.3 grams per cubic centimeter. So if you go back and look, all of these are very, very close to what we know is true or what is the accepted value. Okay, so these would all be very accurate. Like I said, science, there's always human error involved. We know that. And so when doing experiments, you will often be asked to do a percent error to account for how much error there was or why your answers might not either be accurate or precise, just depending on what that error is. So there is a equation for it, and you are going to write it. And percent error equals the experimental value. So that's the one you get through the experiment by you doing it, minus the accepted value. And the accepted value is what we expect as scientists, what we are expecting to get based on calculations and the way the chemical properties of it and how we know they interact and things like that. So the accepted value is either already been tested before in like perfect, near perfect lab settings, or it's been calculated. So we know like what it should be, but we know that's not always the case in actual life. And those two, that value is divided by the accepted again, and then it's multiplied by 100 to get a percentage. Okay, so this number, the experimental number, is the one that you get, the one that you find. That's your value. And then the accepted one is given to you, normally by me. That way, you know what you get, you know what we were expecting to get, and you can kind of see how accurate your answers were. Okay, going down here, we have these 4 bullseyes, dartboard situations going on. You can illustrate these to a certain extent. You don't need all the numbers, or you don't need it to look as pretty, but it's just going to illustrate the difference between accuracy and precision, because we might still be confused. So in darts, or if you're target shooting, whatever, we know that bullseye, or where you want to hit, is this center right here. Okay, that's like worth the most points. So if you have a bunch of dots in the middle, okay, well, you can't really see that. Okay, you're all hitting in and around the middle. That would be an example of high accuracy and high precision. And the reason for that is because all of your points are near each other, so they're precise, yet they're also very close to where we want to be, which is that bullseye. Okay, so this is high accuracy, high precision. If we had a cluster up here, what would it then be? What would our accuracy be? Remember, our accuracy, we want to be accurate or near the bullet, or the bullseye. So are we, if we're up here? No. So in this example, we would have low accuracy. But what about our precision? Our precision Are they all kind of near each other? Are they near the average? Are they near the same point? Yes. So this is an example. It has high precision. You're very precise in where your points are going, but they are not accurate. Okay, another example on this fourth one would be kind of like that, just skirting around the bullseye. Okay, our accuracy. We are a lot closer to the bullseye, so our accuracy is pretty high. And what about our precision? Since they are not very clustered or close together, they're not very precise. They're kind of all over the place, but they're still really close to the bullseye. So it would be high accuracy and low precision. And then finally, what if we had our dots like that? What would that be in terms of accuracy and precision? We have a lot on the outer edges, so they're not really near that bullseye. So this would be low accuracy. And then are they clustered together? Not really. They're not near each other. They're not near an average. So this would be also low precision. Okay, so remember, precisions are all clustered together. They're around the same thing. And accuracy is how close you are to what the accepted or true value is. So your goal is to have it be accurate and precise, but it can vary from that. Okay, and moving on down to everyone's favorite part of chemistry, significant figures. Okay, so let's just think about the word significant figures. So in this case, we're talking about numbers. The numbers are figures. And in chemistry and in science and, any branch of science, you want your data to matter, right? That's why you're doing this. That's why you're conducting the experiment. You're trying to figure out meaningful values. And so significant figures are a way for your numbers to be significant or meaningful. Okay? So significant figures, there's a few things that we'll be covering with them, but significant figures are the values you are certain of plus one uncertain measurement. So when we did the measuring activity, there were numbers that you or your group had to estimate on. You had to use your knowledge of dimensions and properties of basically dividing things up and your experience with that in order to give me answers. So for any of the measurements, there wasn't one specific answer for it because in most of the cases you didn't have whatever you were measuring it with, it wasn't broken down enough. Does that make sense? So like with the stick units, it wasn't a nice easy number like, oh, I'm three stick units tall. Okay, it wasn't that easy. So in your groups you had to estimate that next number. So you knew, okay, 4 stick units tall and then some. And you had to figure out that and then some. Your group had to figure that out. And so when we talked as a class, hopefully you saw that the numbers did vary, but hopefully they were around the same. Hopefully they were precise enough to your measurements so that you could really agree on them, okay? So when we talk about the values you are certain of, that would be like the fact that I was 4 stick units tall and then some. The 4 stick units was the certain measurement plus 1 uncertain measurement, and that's basically the and then some. So yesterday, or whenever we did the measuring activity, we had to estimate the last digit. Okay, so I said get as specific as you can, or get as close to the actual measurement as you can. Okay, so for the stick units, hopefully you thought to just estimate 1 digit. So you were able to say 4, and then dividing it up into tenths, maybe you said 4.5 or 4.6 or 4.7 or whatever. Hopefully you didn't say 4.5756321175, because there's really no way for you to figure out those rest of those estimates. You were able to just estimate basically on that first uncertain measurement. Okay, so this allows you to be certain of one, or the value you're certain of plus that one uncertain measurement. So you won't go out to the thousandths place, just that one uncertain measurement. Significant figures are related to scientific notation, and they're used because your answer can only be as accurate as your least accurate measurement. So I'm going to underline that or highlight that because it's super important. Because your answer can only be as accurate as your least accurate measurement. Okay, so if you estimated just one of the measurements and then you're adding them all together. So let's say you had 3 measurements. 2 of them you did not have to estimate on, they were a certain count. And then the last measurement you did have to estimate for whatever reason. Your final answer is not going to be 100% accurate because you had to estimate that one measurement, okay? So what it's saying here, your answer can only be as accurate as your least accurate measurement. So if you have a super inaccurate measurement, your entire answer is going to be pretty inaccurate because of that one measurement. Okay? So there are a couple rules, and we'll be going over them more. We'll be doing worksheets over it to make sure that we really understand it going forward. So when we are in the lab or calculating things, you'll be able to make sure that your measurements or calculations are meaningful, okay? Which is what the whole purpose of sig figs. So rule number 1, non-zero digits. Non-zero digits are always significant, okay? So for example here, let's say we measured something and it measured 151 centimeters, okay? We measured that and we know that all 3 of those digits are meaningful, so they're significant, all 3 of them. That number, that answer would have 3 significant figures, okay? Rule number 2, captive zeros. So zeros between non-digits are significant. So if a 0 is sandwiched in between 2 non-zero digits, it's going to be significant. For example, if you said you had 207 milliliters, you have 1, 2, 3 sig figs because that 0 is significant. It is meaningful because it's in between those 2 numbers and it's like part of that measurement, okay? This one right here would have 1, 2, 3, 4 significant figures because both of those zeros are captive and located between non-zero digits. Okay, rule number 3, leading zeros. So zeros to the left, we're going to underline that. Zeros to the left of non-zero digits are not significant. Okay, to the left of non-zero digits are not significant. In this example, say you measured something and you got 0.03 meters. These first two zeros are to the left, so they are not significant. They do not count. But this 3 and this 8 count as significant figures. They are meaningful to your measurements. Rule number 4. Trailing zeros. Now this one's a bit tricky. Zeros to the right of non-zero digits are only significant when the number has a decimal. Okay, so that decimal is basically saying, hey, I'm super sure of this measurement. If you don't have that decimal, you're kind of just saying that it was more of an estimate or it was not as accurate as it could have been. So for this first example, you measured something and it was 1.50 grams. Since there's a decimal, 1, 2, this 0 would count as a meaningful number there. Here, that answer is super accurate in that it had that decimal and they were for sure that it was 0, 0. They would not have included those two numbers if they were not for sure that that was the correct measurement or reading. Okay? But the last example is just 2,000 liters. No decimal. So this one is only going to have one significant figure. That 2 is the only meaningful number there. Because those other two, there's a chance that this could have just been an estimation or something. And so we're not, these digits are not as meaningful to us in making sure that our measurement is meaningful. Okay, rule 5, exact numbers. Oh, wrong color. Exact numbers. So this would be counts of animate objects. And an animate object is something that like you can hold, you can see, you can feel, things like that you're like for sure is there. They have an infinite number of sig figs. So for example, if you counted 10 people, those are animate objects. You wouldn't use like this, you wouldn't say, oh, that has one sig fig because there's no decimal, so it's just that one non-digit number. You wouldn't say that. It's going to have however many sig figs. Like, it's not going to feed into that calculation of how many significant figures there are, okay? Because, like, if you counted it, you know that there are 10, and you don't have to be uncertain about your measurement there. In that same realm, 5B, Rule 5B, is talking about conversion factors, and they also have an infinite number of sig figs. So, conversion factors, so say you are converting numbers, if this is your conversion factors to get from centimeters to another unit of measurement, you wouldn't say, oh, my number can only have 1, 2, 3, 4. This one has 5 sig figs. So that's not going to factor in with how many significant figures or meaningful digits that your number or your answer has to have. Okay? One last thing with sig figs. Or with calculations. Going up here. So if you're doing calculations and you are just plugging and chugging your numbers, don't automatically write down all the digits that appear in your answer because it may be wrong. It may be wrong because of the number of meaningful digits you have to put in your answer. So it might spit out, five digits, and you only need a certain number for them. Okay? A couple more rules with multiplication or division, because they're special. The product of those answers can have no more sig figs than the measurement with the fewest sig figs. Okay? So, for this example, you're dividing 0.59 grams by 1.01 cubic centimeters. So if you just put that in on the calculator, you would get this answer. But this answer is way, way more specific than either of these two answers or measurements, calculations you put in. Okay, so right here, you have how many sig figs right here. This 0 does not count. This 5 and this 9 count. So here you have 2 sig figs in this answer. These 2. And in this one, that 1 counts. This 0 counts because it's sandwiched in the middle, and this 1 counts. So the least or the fewest sig figs is going to be 2. So you get this huge, huge answer, but you weren't that specific in the numbers that you put in. So your answer cannot be this specific. That's just math. You are not that positive that that is the answer. So you just go with how many the fewest number has, and that's 2. So you change this to 2 significant figures and get 0.58 grams per cubic centimeter. Okay, with addition or subtraction, the measurement with the lowest decimal value determines the decimal value in the answer. So here we're not concerned with sig figs in addition or subtraction. We're concerned with how many decimals they had, because if they had more decimals, this number is way more specific than this number. This number we know that they're more sure about it. It's more meaningful than this answer. And so we can only be as precise as our least accurate answer, which is this one. So this one only has 1 decimal. So if we did this in the calculator, we'd get 7.8 centimeters. But we can only go with 1 decimal, so we'd round it to 7.9 centimeters. And then this talks about the thing we've already talked about. Conversion factors have an infinite number of sig figs. So basically, you don't have to count those digits, when determining how many sig figs are going to be in your answer. Okay? And now, this is the time in the video when you're going to stop. I want you to stop here, because we're going to do an activity and a worksheet over sig figs, so that we're really confident in our ability to use them moving forward. But the video is going to keep going because I don't want to cut it up into multiple videos. So stop taking your notes for now. If you're uncertain about what to do, ask me. But stop taking your notes for now. Do not start writing for dimensional analysis. I will tell you when to start writing for that. Now and only now should you be coming back to this video to continue. If I have told you, hey, start on the next set of notes, is when you'll start now. Okay? So if you didn't stop up here when I told you to 5 seconds ago, stop right now. If a day has passed or whatever, then we'll continue on with these notes, because it makes more sense to you now that we know more about sig figs and we are confident in our ability to use them. Okay? So we are going to talk about dimensional analysis, or as I like to call it, cake and ice cream, because dimensional analysis sounds no fun. So we can call it cake and ice cream here because that sounds more fun. But dimensional analysis is a method of solving calculations involving various units. Okay? It involves the use of conversion factors, so the fact that we know that 1 liter equals 10,000 milliliters, or the fact that we know that 1 milliliter equals 1 cubic centimeter. Okay? So the way that we're going to set this up, we're going to have a given, and it's going to go in the upper left blank on the grid, which you'll understand what I'm talking about with the grid in a second. So let's go ahead and get started with this example. So this example asks, how many seconds will you have lived when you turn 21 years old? Okay, so 21 years old is our given. We're going to identify that and say, hey, that's our given. We're going to underline that. Okay, so that is going to start up here. We're going to put 21 years. And then we're just going to make a big long line. And then in this bottom portion, we have to do the conversion factor. So we know that 1 year is 365 days. Okay, that's a conversion factor. We know that in 1 day, there are 24 hours. We know that in 1 hour, there are 60 minutes. We know that in 1 minute, there are 60 seconds. Okay, and boom, that is what we are trying to figure out, how many seconds. So we had to figure out the conversion factor for a year to go to days, days to hours, hours to minutes, minutes to second. So we couldn't immediately just go from years to seconds because there are a lot of different units or conversion factors that go in between that. Okay, so now let's make sure all our units, like this bullet says, cancel out units that repeat. So let's cancel these out. So we have year on top, year on bottom. And they have to be on opposite sides of that line. So days is on top, days is on bottom. Hours on top, hours on bottom. Minutes on top, minutes on bottom. Boom, what we have left is seconds, and that is what we are trying to find. So we know we set it up correctly. Hooray. And now, to figure it out, the easiest way to do it is multiply everything across the top and everything across the bottom and divide. So if we do that, and we go down here, because I don't have enough room up top, if we multiplied everything across the top, we'd get 6, 6, 2, 2, 5, 6, 0, 0, 0. And if we multiplied everything across the bottom, we get 1. Okay, so we know that answer is just this number on the top. And we're going to use our unit, which is seconds. So by the time that we are 21 years old, we've only lived 662,256,000 seconds. Doesn't sound like that many, but it's a pretty big number. Okay, so we had our given that went up here. We canceled out our units, and we ended up with the correct units over here. And our number makes sense, right? So if you accidentally hit a button wrong and you only got like 6,000 seconds, think in your mind, does that make sense? And you should come to the answer that no, there are more than 6,000 seconds in 21 years. So recalculate something, because we can make mistakes. We make mistakes all the time. That's why we have to think about making sure our answer makes sense. So for any type of problem solving in this class, because that's one of the main reasons we're doing this, is problem solving. So in problem solving, you're going to ace the problem. A stands for analyze. You are going to determine what information is given and what the problem is asking you to solve and how to get there. Okay? And so if we're going back up here, our information that was given is 21 years old. The problem is asking us to get to seconds. We know that there's no direct conversion factor to get us from years to seconds. Yes, someone's already done the math and you could Google it and get it. But this way we know all the conversion factors are correct if we do it the long way. So we knew how to get there, that we had to go from years to days to hours to minutes and then finally to seconds. The C stands for calculate. You substitute given information into the equation, which was 21 years, and use appropriate conversion factors, which we did, and then you do the math, okay? And then when you get to E, you're going to evaluate. Determine if the answer is plausible. Be sure the unit is correct. We did that. And recalculate the problem with answer as a check. So you could work this answer backwards to figure out if your answer was correct. Okay? So up here, we already aced our problem because we analyzed, calculated, and evaluated without even having to be told. So another thing for problem solving, you're going to do this with every problem. Okay? You're going to list the givens. Up here, we underlined it. You're going to list the unknowns. And our unknowns were how many seconds. You're going to set up the basic equation, which we did here. You're going to substitute values. You're going to provide the answer rounded to appropriate number of sig figs. And you're going to provide the answer with correct units. You'll hear me call this GUBSAC. Okay, so you know that you're given unknowns, basic equation, substitute values, answer provided to appropriate number of sig figs, and correct unit. Okay, it's a made up thing, but go with it because you're going to have to do it. Because for certain problems, you will have basic equations. Like I wouldn't call this a basic equation, like we had to figure this one out. But there are basic equations that we'll talk about it a little below. But up here, we did those three things. We substituted our values. And then let's look at the A. Answer rounded to appropriate sig figs. So if you waited to listen to this video, you've already done the sig fig worksheet. Hopefully you have a pretty good understanding of it. And you're like, well, Miss Sager, this number has way too many sig figs. Like the smallest number of sig figs up here is 1. This 1 is just 1 sig fig. But remember, up here, this bullet, conversion factors have an infinite number of sig figs. So if we're using conversion factors, we don't have to count those. And all of these are conversion factors. So this entire problem is based out of conversion factors. So we don't have to regard that number of sig figs because we are for sure with these answers. So we can be for sure with our answer there. Okay? But I'm glad you thought about sig figs up here. And then we provided our unit because no naked numbers. But more conversion factors down here. I do want you to write these down because they are very important. Otherwise, I wouldn't have included them. There are temperature conversions. In science, we typically work with degrees Celsius because we're scientists. But there's this other temperature measurement that we will use when we start working with theoretical problems and things that we're like not measuring, because we can't really measure Kelvin, but we can work with Kelvin. So if we're trying to find the temperature in Kelvin, we have what it is in Celsius, and then we add 273 degrees. Okay, so for example, if we were trying to figure out the temperature in Kelvin of our human bodies, we would add 37 degrees Celsius plus 273, and we'd get 310 degrees Kelvin. Okay, if we had Celsius instead, and we wanted, or if we had Kelvin instead and wanted to get to Celsius, we'd just do the opposite and subtract. Your length, so 1 kilometer is equal to 0.62137 miles. Miles can be converted into feet and kilometers. Inches equals exactly 2.54 centimeters. So all those are conversion factors, so we do not have to be concerned with sig figs there. Some other common equations that you'll probably need. Density is just mass divided by volume, illustrated that way. And then the units for density are grams per milliliter or grams per cubic centimeter. Okay, so this sums up your measurements and calculations notes. Congratulations, we have finished the first unit of chemistry.